You had to admire people that would devote years and years and years to trying to do it, with the likelihood being that they would fail.
Prije više od 2 desetljeća, dvije su ekipe odlučile pokušati nešto naizgled nemoguće. Dokazati postojanje crnih rupa.
Both of these kind of converged at almost the same time, but coming about it in very different ways.
We're crazy optimists in this business. You have to be. If you look at all the things that could go wrong, then why would you dedicate your career to it?
Jedna ekipa nazvana LIGO naumila je velikim instrumentima, takozvanim laserskim interferometrima, otkriti sitna mreškanja u prostor-vremenu, zvana gravitacijskim valovima, prouzročena stapanjem dviju crnih rupa.
Albert Einstein thought that it will be impossible to ever detect them.
We're looking for motions that are about 1,000th of the size of a proton inside the nucleus of an atom.
Druga ekipa, nazvana teleskop događajnog obzora, pokušat će snimiti fotografiju crne rupe, što je zadaća usporediva s pokušajem opažanja teniske loptice na mjesecu.
And so you need a telescope the size of the entire Earth.
But obviously, we couldn't build a telescope the size of the Earth.
But in radio astronomy, you can play this near magical trick where you take 2 telescopes separated by some distance, bring the data that they receive together to form a telescope as though you had one as large as the distance between these telescopes.
Pronalaženje crnih rupa, tako da se koja od njih snimi kamerom ili bilježenjem gravitacijskih valova, bit će jedna od najvećih zadaća u povijesti znanosti.
I was sort of trembling in front of the challenge.
It was hopeless because the technology would never be there.
We staged experiments that went nowhere. We tried and we failed.
Uz to, ako pronađu ono što traže, hoće li to moći zadržati u tajnosti dok ne budu posve sigurni?
Many people had a eureka moment.
I was completely blown away by how clear-cut this signal was.
And I had a moment of panic.
We all kept the results secret.
Because I knew if that was right, we would be writing history.
All I could do was figure out how we had gone wrong. How are we fooling ourselves?
At some point, you have to stop and just listen to the universe.
Crne rupe najprije se spominju u teoriji, možda i postoje, ali za to nema jasnog dokaza. Mnogi su samu ideju smatrali krajnje manjkavom.
An extremely massive object will curve the space-time around it so much that anything that passes by will actually fall into that object and will not be able to escape. Even light wouldn't be able to escape, and that's basically a black hole.
But is this real? Clearly, something like this would not occur in nature.
No one felt that nature would be that crazy.
These cosmic objects are more extraordinary than we could ever have dreamt up.
At the center of a black hole, the laws of physics as we know today, they break down.
There's no matter there. The structure that we see is a vacuum structure. It's like a tornado in space-time.
Zamisao o crnim rupama u njihovu najčišćem obliku potječe od Alberta Einsteina.
For physicists, the great year for Einstein was 1905, when he solved several of the biggest problems in physics within a matter of months. And then he spent 10 years developing his theory of gravity, which was general relativity.
What we see coming out of general relativity is that matter and energy has the ability to affect the space-time around it.
Prostor, vrijeme, matematički je pojam u kojem se vrijeme stapa s 3 dimenzije fizičkog prostora, pa su tijesno isprepleteni u tkivo prostor vremena. Stvarna prisutnost materije iskrivljuje to tkanje.
If you send a light beam past, say, a star or a planet, the reason it bends is because it's trying to follow the straightest path possible in a geometry that is now curved. And thus, that is what gravity is. It's basically the geometry of space-time.
Nekoliko tjedana nakon što je Einstein objavio svoju revolucionarnu teoriju gravitacije, ljudi su počeli ulaziti u srž značenja svega toga. Među prvima je bio njemački fizičar Karl Schwarzschild. Iako je bio u 40-ima, Karl se u Prvom svjetskom ratu odlučio prijaviti kao dragovoljac i služio je kao topnik.
He was able to predict how space and time would look like around a point mass.
And he realizes if you compact matter into a small enough volume, that there's this event horizon at what we can now call the Schwarzschild radius, where the speed of escape is larger than the speed of light, where even light cannot make it out.
A one-way boundary where information and light can only go in but never can come out again.
That's the moment when black holes really were born.
Now, of course, a completely crazy idea. This wouldn't exist.
Neither man realized that it was anything more than a mathematical construct that they didn't really have to worry about because no one felt that nature would allow it to happen.
Poor Karl Schwarzschild, he died very quickly after finding the solutions due to an illness that he got in the trenches there.
Tijekom 20. stoljeća među znanstvenicima je teorijsko proučavanje crnih rupa postalo popularno i to su aktivno činili. Iznosili su teorije o tome kako one nastaju, a astronomi su čak počeli nagađati gdje bi mogle vrebati u svemiru.
So there are two varieties of black holes. The stellar variety, which are born during the death of stars, and they weigh a few or 10 times what our sun does.
Vjeruje se da Schwarzschildov polumjer crne rupe zvijezdane mase veličinom odgovara otprilike modernom gradu. Iako im je masa jednaka onoj 10 ili više sunaca, sitne su u usporedbi sa zvijezdama iz kojih su nastale. Supermasivne crne rupe imale bi ukupnu masu kao milijuni ili čak milijarde sunaca. Prema Schwarzschildovu izračunu, radijus bi mogao biti velik poput cijelog sunčeva sustava. Astronomi su se zapitali kriju li se zvijezdane crne rupe u svim galaksijama i mogu li se one supermasivne pronaći u središtu mnogih od njih. Supermasivnu crnu rupu, koja bi eventualno bila u središtu naše galaksije, čak su nazvali zvijezdom strijelac A.
Are they out there? The theory predicted it, but are they really real?
U potrazi za odgovor na to pitanje ekipa LIGO pokušala je pronaći manje crne rupe s gravitacijskim valovima. Ekipa događajnog obzora za to bi vrijeme tražila supermasivne crne rupe, oslanjajući se na astronomiju koja se služi radijskim valovima.
If you have optical light, the wavelengths are tiny, tiny, tiny. But if you study radio emission, the wavelengths are actually big. And so you have a gigantic dish that can reflect radio waves.
Astronomi su zbog intenzivnih radijskih emisija koje dopiru iz središta galaksija zaključili da bi razlog mogle biti supermasivne crne rupe.
So we had to think a little bit about these emission mechanisms. Like what would cause this glow in radio waves? And so what can power something like that is gravitational accretion onto a supermassive black hole. That's the only way we know of to power something like this.
U 20. stoljeću ideja o snimanju crne rupe s pomoću tih radijskih emisija nadilazila je tadašnje mogućnosti, no neki su se usudili maštati.
Many times in science, you wind up in a situation where somebody makes an initial discovery and it goes underappreciated. And this is the case with Jean-Pierre Luminet. I mean, this was a real visionary. In 1979, he came with the first full simulation of what a black hole would look like if you were there, like if you could really see in infinite detail.
Za snimanje prave crne rupe, onako kako je to zamislio Jean-Pierre Luminet, bio bi potreban radioteleskop s antenom veličine planeta Zemlje, te tehnologija koje tad još nije bila. No ekipa gravitacijskih valova morala je riješiti jedan još elementarniji problem. Nitko nije ni znao jesu li gravitacijski valovi uopće stvarni. Teorija o njima potekla je od Alberta Einsteina otprilike u isto vrijeme kad je Karl Schwarzschild formulirao svoje ideje o crnim rupama.
In 1916, Einstein wrote a little paper 5 pages long, maybe. He looked at the equations of general relativity that he had developed, and he noticed it had a great similarity, if you put it in a certain way, to the equations of electricity and magnetism. And since electricity and magnetism have waves, he conjectured that gravity must also have waves.
Einstein je prije 30 godina prošlog stoljeća napisao još 2 rada o gravitacijskim valovima.
According to Einstein, this phenomenon, gravitational waves, is very interesting from a theoretical point of view, but any real effect on Earth will be so small that it will be very likely always impossible to ever detect them.
They were never fully accepted during this whole period and beyond, even until his death.
Veliki Albert Einstein umro je 1955. Crne rupe i gravitacijske valove, pojmove koji su vukli korijen iz njegovih teorija, tad se uopće nije smatralo stvarnim pojavama. Ali 1958. 50 najvećih svjetskih stručnjaka za opću teoriju relativnosti održalo je sastanak.
So at this now renowned conference, the question of whether gravitational waves really do exist and produce something that could be measured was raised.
Richard Feynman was there. He said if gravitational waves really exist, they have to be able to do something. They can't just exist. They have to be able to transfer energy. And so he made what we call a Gedanken experiment, just a thought experiment. And that was if you have a bar and you put a couple rings on it, and then a gravitational wave goes through the bar, it'll take the bar and it'll expand it and contract it and expand it and contract it at the frequency of the gravitational wave. As it expands, it of course pushes on the rings and they would move. But what's happening is that they're transferring energy, friction, to the ring.
Taj pametni misaoni eksperiment nadahnuo je jednog od sudionika sastanka da osmisli takav uređaj. Zvao se Joseph Weber, a naprave koje je izradio zovu se Weberovi cilindri, prvi detektori gravitacijskih valova.
It's accepted today that his bar detectors were not sensitive enough to be able to make any detections, but he played a very important role in sparking the rest of the world's interest into what a different type of detector might look like that could ultimately be more sensitive.
So gravitational waves, if they exist, how do they manifest themselves? If I take just a place and a gravitational wave comes through, it distorts the space and time such that it stretches it in one direction and squashes it in the other direction. The easiest way to think about it is what happens when you go to the amusement park and you see these mirrors. You look in one and you get tall and thin, go to the next one, you get short and fat. If you imagine that you're now a detector, it's basically going back and forth between those two mirrors. You're getting taller and shorter and fatter at the frequency of the gravitational wave. So maybe the gravitational wave is 60 hertz. So 60 times a second you're going and that's what we have to measure. So how are we going to measure that?
So we had to find out a way to be able to detect here on Earth some very, very small perturbations. And it turned out that the most sensitive instrument that we could make and design is what is called a laser interferometer.
So what does an interferometer do? I take a beam of light and I get to a place where there's a mirror that sends half the light in one direction and half the light in the perpendicular direction. If somewhere down the way I put a mirror, it'll bounce back. And if I've calibrated it so they're the same length, they'll come back at exactly the same time. If I invert the signal from one to the other, they'll exactly cancel. I have a little photodetector, it sees nothing. Okay. But now imagine the gravitational wave went through the same thing. Then 60 times a second, one arm's going to get a little longer than the other. The light will come back at a slightly different time, and the light will go 60 times a second, depending on how strong the gravitational wave was. And that's all we have. We have a detector that's measuring the length of these two arms. That's called interferometry.
Dvojica koja su vjerovala da bi rješenje za detekciju gravitacijskih valova, tako i za detekciju crnih rupa, mogla biti interferometrija, bila su Rainer Weiss s MIT-a i Kip Thorne s Caltecha.
started on the faculty at Caltech as a particle physicist at the same time. Kip Thorne started as a general relativist, and we were close friends.
Do 80-ih nekoliko je skupina iz cijelog svijeta počelo razmišljati o izgradnji interferometra radi traženja gravitacijskih valova. Britanci i Njemci dogovorili su suradnju. Talijani i Francuzi započeli su zajednički projekt Virgo, a u Sjedinjenim državama Rainer Weiss, Ron Driver i Kip Thorne osnovali su LIGO. Ali dobiti sredstva za provedbu takva pothvata nije lako.
What was pointed out in the US Congress about whether to appropriate funds was just how extraordinarily sensitive these detectors would have to be. You would need to be able to measure these mirrors moving at distances that were some 10,000 times smaller than the diameter of an atom. And when thinking about that in an astronomical terms, that's maybe, say, the same as being able to measure the distance to the nearest star and being able to say definitively whether that distance has changed by the width of a human hair. And so these mind-boggling ideas were used as a way to cast doubt on the plausibility of such an experiment.
1990. Nacionalna zaklada za znanost odobrila je gradnju dvaju detektora. U Livingstonu u Louisijani i u Hanfordu u državi Washington. Ali za LIGO je trebalo još mnogo novca i odlučno vodstvo da bi bilo ikakvih izgleda za pronalaženje zvijezdane crne rupe s gravitacijskim valovima. Ekipa teleskopa Događajni obzor, koja je nastojala snimiti sliku supermasivne crne rupe, službeno se neće okupiti još niz godina, iako su se već pojavile ideje na kojima se temeljio njezin rad.
When I was in graduate school, I had the great fortune to work with Dr. Alan Rogers, who was one of the pioneers of radio astronomy. And he got me hooked on using interferometry to make the most detailed images of the sky that we could make at the time. And we started doing this with Sagittarius A star, which we thought was a supermassive black hole in the center of our Milky Way galaxy.
So there's a technique out there that helps us with increasing the resolution that we can get from a telescope, which is not to use a single one, but to use pairs of telescopes and look at the distant object at the same time with these pairs of telescopes, record the incoming light, and because we time tag exactly when each signal arrived, we can, after the fact, combine these signals using supercomputers, just match them up and pretend we have the resolution of a telescope that's as big as the separation between the two. We call it very long baseline interferometry. And the key thing here is that we interfere the signals that we receive on different parts of the Earth.
Primjena dugobazične interferometrije, skraćeno VLBI, za snimanje slike supermasivne crne rupe, zahtijevala bi velik pomak u našem razumijevanju načina na koji se materija vrti oko crne rupe, koja je privlači te nastaje takozvani akrecijski disk.
I think any revolution requires a group of people sorting out the ideas that they have, figuring out what's the best way to move forward.
I met Dimitrios when we were both at Harvard. In fact, our first paper together is on Sagittarius A star, the emission from it, and whether the accretion flow around the black hole would allow us to see down to the horizon.
It was a time where we had just started thinking differently about how do black holes accumulate matter from their surroundings. For about 20-30 years, there was a paradigm, but then it became obvious sometime in the 90s that that paradigm was not right. So it was that small group that started building a new paradigm.
We were doing this theoretically. We were thinking about where does this radio emission come from in black holes? Some people proposed that this would come from the matter that shoots out from the plasma jets. And other colleagues were calculating that the radio emission would come from the matter falling into the black hole.
We had group meetings that lasted 8 hours. We just had coffee, we just had a whiteboard, and we were trying out ideas. And most of them were wrong, most of them failed. But a few of them turned out to be really important. One of those questions that we wanted to ask is, what would the black hole look like if I were to take a picture? Will it be a big fuzzy fluff of cloud, or will it be something really small as the event horizon of the black hole? So we spent about 10 years learning how to tweak the theory and make predictions of black holes that were not the same as the ones that Albert Einstein predicted.
And lo and behold, we always saw this dark shadow in the very center. Irrespectively of how the matter was rotating, whether it was falling in, whether it was flowing out, whether the black hole was rotating, as long as the mass was known as a black hole, the shadow had to be there.
So in year 2000, I realized that at certain wavelengths, the entire accretion flow is actually transparent and allows us to see all the way down to the horizon of the black hole, which is what we're after, that shadow.
How would that look like? Could we actually see that?
And it turns out that the answer depended on how did I take the picture, what wavelength of light did I use.
Ta novonastala međunarodna zajednica radioastronoma i teoretičara uvidjela je da je ključno usredotočiti se na dugobazičnu interferometriju kako bi se zabilježile više frekvencije svjetlosti.
The higher frequency you observe, the finer your angular resolution. Your pictures get much crisper and you can see the details that you want to see. But the second thing is that as you move higher in frequency, you can see more deeply into all the hot gas. So you really want to see all the way to the event horizon. You want to get sharper images, and that pushed us to higher frequencies.
Meta na kojoj su se svi fokusirali bila je navodno supermasivna crna rupa u središtu naše galaksije, strijelac A zvijezda.
I was convinced we would be able to see the black hole in the center of our Milky Way with a global telescope array. But that required a lot of money, new telescopes, new receivers, and it required a big community to work together.
There's a transition that many areas of science go through in terms of moving from things in the laboratory, taking those ideas and concepts and scaling them up. To turn those into a large-scale project, it's a skill in itself.
Barry Barish bavio se fizikom elementarnih čestica u superprovodljivom supersudaraču u Teksasu.
The US Congress canceled the super collider at a time when LIGO needed somebody that was capable of taking it to get both the funding that was needed and be able to put it together in a way that would make it work.
Godine 1994. Nacionalna zaklada za znanost imenovala je Barisha voditeljem laboratorija LIGO.
About 6 months later, went to the National Science Board that oversees the National Science Foundation and convinced them, and they funded us. I think the real hero is not me, it's the NSF. For me, the big issue was to get a strong enough team. As good as these two institutions are, Caltech and MIT, for our problem as hard as gravitational waves, we needed to tap the best people in the world.
The underlying technologies that are relevant for gravitational wave detection were being developed in different places.
Godine 1997. Barish je pokrenuo znanstvenu suradnju, pa se LIGO pridružilo nekoliko međunarodnih skupina. Sad su postojale dvije velike multinacionalne skupine koje su se utrkivale u izradi detektora LIGO i Virgo. Napredovala i skupina koja će postati teleskop događajnog obzora.
So we all started to work together at 3 millimeter wavelength. And then we realized that to push it even further, we had to go to 1 millimeter wavelength. And that's when we began this real race, a competitive but also a collegial race. You know, could we push this technique to its real limits? And that was a great time. And then we ran into this roadblock. For many years, we were stymied. We were just stuck because we didn't have the sensitivity we needed to make these observations at high frequencies. As soon as you go to high frequencies, everything becomes harder. The atmosphere reduces the signal coming from black holes. The superconducting cameras that we mount on each of our telescopes to receive the radio waves from the black hole, they become more noisy. So everything is working against you. The one thing that we had, our secret weapon, was that we could increase the bandwidth. Starting at around 2000 and going till about 2006, there was this explosion in capability that happened because we started building our instruments out of commercial electronics. Imagine that. Up until that point, we had been developing specialized instrumentation that took a decade to design and manufacture and get into the field because it was so exquisitely specialized.
Grafičke procesorske jedinice ili GPU-ovi specijalizirani su računalni čipovi koji se ponajprije upotrebljavaju za videografiku.
We weren't pushing the development of GPUs. In fact, the gaming industry was. But we thought, hey, we can solve Einstein's equations on these things, and we can do it much faster than with traditional CPUs.
Isto je vrijedilo i za pohranu podataka. Trgovački tvrdi diskovi postali su sve brži i imali su sve veći kapacitet.
All of a sudden, we could go to the store, buy components, hook them together, and we could make something that was 10 times more capable, 10 times lower cost, and we could design it 10 times faster. It was nothing short of a miracle.
LIGO-vi detektori morali su biti najosjetljiviji znanstveni instrumenti na svijetu. I to zato što je naš planet tako bučan.
Much of the good work happens at night, and that's simply because the environment around you is quieter at night. There are fewer cars driving on the road, hitting bumps and causing the ground to shake. People felling trees that are falling down in the forest. The operation of heavy machinery nearby is also lower at night. There's also natural effects. Of course, earthquakes are an obvious consideration that might jump to many people's minds.
Believe it or not, even if you're in the center of a continent, there is a peak of motion that occurs at very low frequency due to waves beating on the ocean shore.
The reason that all of these sorts of things matter is because ultimately these mirrors that we're trying to detect very small motions of are connected to the ground.
The Earth, the ground, is shaking all the time by about a millionth of a meter, which is a million of a millionth times more than what we're trying to measure. So this is one reason that our system cannot just sit on the ground, but our mirrors are the most quiet place on Earth.
The beam splitter itself is a mirror, big piece of glass, suspended on wires. That has to be isolated from external disturbances, so it's housed inside a vacuum tank. That vacuum tank is inside a big building. Out from that building go two arms. Inside that arch there's a vacuum pipe. Inside that travel the laser beams that travel the length of these 4-kilometer arms. The ends of the arms inside those buildings, there are vacuum tanks. Inside those tanks are some isolation systems that isolate from ground vibrations mirrors that are suspended in the initial incarnation of LIGO on metal wires.
LIGO ne vodi borbu samo protiv vibracija i buke, nego i protiv jedva zamjetljivih kvantnih efekata.
To measure precisely how the two waves get together, you have to measure how many photons hit your detector. But since the number of photons is what we call a quantum variable, there's an intrinsic uncertainty there. We cannot do better than what the Heisenberg uncertainty principle dictate. That's one reason we need very powerful lasers.
As we increase the laser power, the force exerted by the light on the mirrors also increases proportionally. So that becomes one of the big challenges of increasing the laser power.
Every time a photon bounces off our suspended mirror, it transfers some momentum to the mirror. It gives it a kick.
If it were to strike it off-center, it's going to actually create a torque. The light causes the mirrors to twist. In an ideal situation, you would have the light striking the center of the mirror.
So to be able to understand more about black holes and big stuff out there in the universe, we need to understand very well the physics of the quantum mechanics and the thermal motion of the atom, which is very small scale physics.
In 2006, we fielded these new electronic systems for the first time. And we took them to two sites, one in Arizona, Mount Graham, and one to Mauna Kea in Hawaii. We set up this experiment, but we were really flying a bit by the seat of our pants. So back at the correlator, we played these data streams from Hawaii and Arizona back again and again and again. And we searched for months, and it was a heartbreaker. After months, we threw in the towel, and we realized that we were just not going to be able to detect Sagittarius A star. Later, we found out why. A small little chip of metal had fallen into the heart of the superconducting junction in the receiver of the Caltech submillimeter observatory. We were able to go back the next year, adding a new site in California. And this time, we were successful. We got the detections. And that showed us immediately that we were seeing horizon scale structure. That's the moment we knew that we could make an image of a black hole.
Ekipa LIGO-a bila je sigurna da ima funkcionalne detektore. Ali ako negdje u svemiru crne rupe dolaze u dodir, nisu to zamijetili.
You don't know that you don't see something until you look for a while. And so it would run for 6 months or a year and wouldn't see any events. We'd turn off, lick our wounds, put in some improvements, and then run again.
But I think that is also maybe part of the excitement. So there was years and years and years of continually improving the detectors, collecting data, improving them, collecting data, and no detection, no detection, no detection.
There were times where myself or the community thought that maybe we got ourselves into something too big.
The initial version of LIGO wasn't good enough to see gravitational waves, it turns out.
2010. detektori su se trebali ugasiti u pripremi za veliku nadogradnju pod nazivom napredni LIGO. Ekipa koja je trebala proizvesti sliku crne rupe shvatila je da kolegijalno natjecanje između nekoliko europskih i američkih institucija neće biti dovoljno.
We would need many more dishes. We would need the European dishes, we would need the American dishes. So it was clear at some point those different efforts had to come together and merge into a global collaboration. And so there was a meeting in 2009 in California, and I was sitting there at a coffee break together with Shep Dolman and was saying, if we want to get this funded later, we can't just keep talking about sub-millimeter VLBI array, blah, blah, blah. Nobody will understand what it is. We have to give it a flashy name. What about if we call it Event Horizon Array or something like this? And in the end, we came down to Event Horizon Telescope. And that's how it started.
Teleskop Događajni obzor napokon je i službeno predstavljen. Za to vrijeme LIGO je bio usred nadogradnje s početnog LIGA u naprednu inačicu.
We wanted to build a very sensitive instrument, and that meant that we had to take some risks, if you want.
U nadogradnju naprednog LIGA uloženo je mnogo truda, a posebice u zrcala i načina koji su bila izolirana od ostatka svijeta.
So instead of suspending these mirrors on metal wires, we were actually suspending them on glass fibers, fused silica fibers.
Those fibers, they're very strong if you pull them, but if a grain of dust hit them, they shatter.
Možda najveće tajno oružje za kojim je ekipa LIGA posegnula da detektore izolira od neželjenih vibracija, bila je tehnologija koja se primjenjuje u slušalicama s poništavanjem buke.
You put on these earphones on an airplane and the roar of the engines goes away and you still hear the stewardess ask you, do you want coffee? So what it does is measure the ambient noise of the engines and cancel it. But the stewardess talking to you is not ambient, it's a signal. And so you hear that fine. So the idea was to bury inside of these shock absorbers little seismic sensors that measured any residual motion of the Earth. And then we just push back against it. You know, make little actuators that push and cancel the residual motion that's there after the shock absorbers. And that gained us a factor of 10 in sensitivity.
Skupina teleskopa događajnog obzora počela je razmišljati o mogućnosti snimanja još jedne supermasivne crne rupe, a ne samo strijelca A zvijezde.
There was another black hole out there which was 1,000 times further away, but also 1,000 times more massive.
M87 je galaksija oko 54 milijuna svjetlosnih godina udaljena od Zemlje i upravo kao i Mliječna staza, vjerojatno da se u njezinu središtu nalazi supermasivna crna rupa, samo znatno veća.
M87 is so massive that it doesn't change during the course of an evening, whereas Sagittarius A star is speedier, and during the course of a night it changes its appearance.
Napredni LIGO-vi detektori sada su uspješno nadograđeni i pokazuju mnogo veću osjetljivost u odnosu na sve dotad postignuto.
When we start a data run each year when we do this, there's a little period of time when people who are expert on particular things can still decide to make some changes of settings. So we call it an engineering run. It happened during that period.
can imagine that I can remember very well that day. So it was a Monday, and I remember that because that was the day after I ran my first marathon, so I was thinking that was enough excitement for a while, right?
I remember quite vividly in my office in Glasgow when our colleague suddenly said, "You do know the signal had just arrived?" And we were like, "No."
My colleague came to tell me that it seems there's been a detection. I just brushed this comment off. To me, it seemed, oh, like we're not even in the observation run yet. It's too early for this to actually happen.
When that event happened, it happened 7 milliseconds earlier in Louisiana than in Hanford.
And my first thought was, this can't be real. This is too good to be real.
And you have to imagine, for people who've spent decades measuring noise, and being very good at measuring noise, to have a signal arrive and it be large, it really did take people by surprise.
Izračunato je da je detekcija od 14. rujna 2015. nastala spajanjem dviju crnih rupa zvijezdane mase udaljenih 1,3 milijarde svjetlosnih godina od Zemlje.
We were expecting to have to fight our way through a lot of justification to convince people that we really had seen gravitational waves. But that was exactly what you would expect out of a textbook. So the first thing I thought is, this is not real. Somebody did this. Because at the time we had a program which was called blind injections to test if we were actually able to detect gravitational waves. Some people, without telling anybody, would add on purpose fake signals. So all I could think is that, great, this is an artificial signal. But we got words from whoever was in charge of this blind injection saying, no, we didn't have time to set up this whole system. Sorry, we're late. So this is not a blind injection. But that was not the end of the story. That was the beginning of maybe 6 months of very hard work to try and prove that we didn't do anything wrong. No, because you don't want to cry wolf the first time you detect the gravitational wave, because that had happened in the history, in the past, so we don't want to do that, because then you lose credibility, of course.
I think for many people, justifiably, after many years, they had a eureka moment. And I had a moment of panic. All I could do is figure out how we had gone wrong.
Slijedilo je bjesomučno i užurbano razdoblje u kojem je vjera u dobivene podatke podvrgnuta forenzičkoj analizi.
After a month we met and we decided it was real, and I thought it was real.
That moment of looking at the data really kind of made me jump.
We kept it quiet, even though we have 1,000 people.
We had one office with several students in it, and all of them apart from one were in the LIGO collaboration. So this poor one student, for about 6 months, every time he walked into the office, everybody stopped talking. And he just must have been wondering what he had done wrong. Was it him? Was it me?
Barry i njegova ekipa dogovorili su se da će rezultate objaviti u časopisu Physical Review Letters prije Božića 2015.
We had our final meeting to decide that it was ready to go, but it hung up in that meeting. We couldn't agree to publish it. So why? Basically, we argued over adjectives. Is the title Discovery of Gravitational Waves? Is the title Evidence for? Anyway, we hung up on this, and so it took us another, week. And then we called Physical Review Letters. And they said, oops, it's too late. It's too close to Christmas. So we said, okay, then we're not giving it to you till after Christmas vacation. I tell this story because on December 26th, Boxing Day, we saw our second event.
Samo 3,5 mjeseca poslije prvog otkriveno je još jedno stapanje crnih rupa.
And even though I had gone through all this intense fall and was absolutely, I thought, convinced, seeing the second event was a sigh of relief in me. I didn't anticipate it, but there's something about confirmation, no matter how much you look at something and believe what you've done.
U veljači 2016. LIGO je u suradnji s Virgom objavio svijetu.
Ladies and gentlemen, we have detected gravitational waves. We did it.
the discovery of gravitational waves. Probably the greatest discovery since we first learned that the universe was expanding. Not only do we now have to believe in black holes, we have to believe that they collide too.
Seeing the first detection of gravitational waves while we were still in the thick of doing the Event Horizon Telescope observations was awesome, was remarkable.
There's always been a little bit of friendly competition with the LIGO team, although I would say that I think people didn't appreciate how close we came. We accreted new partners from Europe, new partners even from Asia, and we all began to work together. And finally, in 2017, we were ready.
Ali u vezi s teleskopom koji pokriva cijeli planet postoje jedinstveni problemi i to frustrira.
With normal astronomy, you need good weather at just the telescope that you're observing with. But for very long baseline interferometry, you need weather to be good all over the globe.
And I was going up to the 30-meter dish at Iram, but it was perfect weather. And it was perfect weather all around the world at the other places. And I said, this can't be. We have good weather here. And I was just nervously looking at the hard drives and the equipment, but all the equipment was working.
At each of these telescopes, we have what's called a hydrogen maser that time tags the data. It's digitized, stored on a hard disk drive, and they're sent by trucks, by planes, to a central facility where they're played back.
The first data was coming back to Haystack, and they were doing the first correlations, and the first success messages came. These two telescopes work together. These two telescopes work together. And after a few weeks and months, we knew it probably worked. We didn't know what it was showing us.
That moment of joy and epiphany came when we saw the data making this ringing pattern.
And it was a curve of data going down, going up again.
Just looking at it, we thought, we have a ring.
If that's true, we're really lucky.
Oh my God, this works.
Kad se prikupe svi podaci sa svih radioteleskopa, može početi postupak nastajanja slike.
And so what they do is they take the light that has been frozen at every one of these telescope sites and they play them back together and they average it down so much because there's only a tiny little signal riding on a huge amount of noise. You get a little nugget of information that's passed on to the imaging algorithms, and that little nugget is what we use to make the picture. But the problem is we're not collecting light from everywhere. There's a lot of holes now. And so the big challenge was taking that sparse and noisy data and using it to recover an image. It's very similar to if you're listening to a song being played on a piano that has a lot of broken keys. And even though a lot of the keys are broken, a lot of times you can still try to make out what the song is. The problem is what we call ill post. There are many different kinds of images that correspond to the same data that we measure. And so we wanted to put all that aside and just say, ignoring all of our ideas of general relativity and all the ideas that we believe right now as far as what we think a black hole should look like, and just see what is the data telling us. Does the data say that there should be a ring? How about a disk? How about, an elephant?
It would be very easy within a collaboration of this size to have 3 different imaging techniques, for example, and to decide that one of them was the way to go. But that would have created a problem because proponents of the other 2 methods, which might be also very, very good, would have felt left out. So we adopted this method of using all of these different techniques as checks and balances. We allowed everyone to proceed with their particular algorithm, their particular imaging method.
And we worked in isolation with our teams for 7 weeks, trying to make what we thought was the best image from the data. And after those 7 weeks, we actually all gathered together in Cambridge, Massachusetts, and we revealed those images to each other. But no matter what, even though the different teams resulted in slightly different images, the same underlying structure was there. This ring of roughly 40 micro arcseconds that was brighter on the bottom than the top. But even at that point, we weren't sure. And so what we did is then we spent the next couple months essentially trying to break our images. So we took the data and we trained our methods. We figured out what were the hyperparameters, what were the knob settings of our methods to recover things like disks instead. So we generate a disk on the sky as if the Event Horizon Telescope were seeing a disk with no hole in the center. And then we transfer those exact parameters onto the real M87 black hole data. And although we had tried our hardest to find parameters that would recover a disk with no hole in the center, we saw that when we used those parameters on the real black hole data, the data forced us to put a hole there. Although each individual image looks slightly different, that ring structure is consistent across all of them.
That's when we knew that we could then come with a real scientific publication and a real press release to announce that we'd seen the first image of a black hole.
The image had to be released all around the world at the right moment. It was all timed to the second.
And for that, Professor Heino Falke is here.
Still have to...
We all knew in July of 2018 what we had.
Dr. Shep Doleman, EHT's director.
And from that time until April of the following year, nobody breathed a word of it. We all kept the results secret.
Now I have to fill the time, actually, until we're allowed to actually, start the unveiling sequence.
Despite all the struggle, all the exhaustion, we kept it under the lid until we were able to really release it.
And even up to the day we made the announcement, everyone thought that we were going to say something about Sagittarius A star, when in fact we had imaged M87. In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. It's called Messier 87 or M87. And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is.
This is the first ever image of a black hole.
We all expected a lot of good reaction from the public, but I think we were all extremely surprised by how quickly it became a classic, it became the iconic image of a black hole.
And this is the strongest evidence that we have to date for the existence of black holes.
When I saw that picture, I just thought that that was the most beautiful photo I've ever seen.
I picked up the New York Times, as I do every morning, and there was this beautiful picture of a black hole.
But I just didn't see it coming. And then suddenly there were these pictures, and I was like,
Nobody had ever seen a black hole. At some point, seeing is believing.
Some people think of black holes as being frightening and confusing objects, but I don't. I'm in love with them. I have no problem cozying up to black holes for the simple reason that they are the one way we'll be able to understand how gravity and quantum mechanics ultimately have to join forces.
Physics is a terribly embarrassing field. We've got two wonderful theories, and never the twain shall meet. One works very well, predicts almost anything that you can do at short distances, and the other one predicts almost anything we see in relativistic astronomy.
Most of the time, gravity is completely separate from quantum mechanics. Gravity is so much weaker than the quantum forces on the nuclear level. The black hole is the one place where gravity plays with all the other forces on an equal footing.
When you're getting close to the singularity, maybe you actually never get to the point where you have an infinite density, because in quantum mechanics, you cannot have something infinitely small because you will always have space-time kind of fuzzy around that size. But maybe what's happening there have some effect at the level of the event horizon. And that's where we can probe with gravitational waves. Because when two black holes collide, the two event horizons, they merge, and they are very excited and are shedding a lot of energy. The shape of the gravitational waves that come out might carry a little bit of information on what's going on inside. Might, we don't know. But maybe we will find out soon.
Einstein nije ni pomišljao da možemo ući u trag gravitacijskim valovima, kao što nije vjerovao ni da crne rupe uopće postoje, iako su proizašle iz njegovih teorija. Sad pouzdano znamo da postoje i da nam mogu otkriti unutarnje zakonitosti svemira.
And that's why black holes draw us, because they represent what we don't know, and they represent what we could know.
If I were to meet Einstein today, I would tell him, hey, Albert, I'm sorry, we proved you wrong.